This video provides an overview of the game scene level I produced for the Game Engine Architecture module. The scene includes a skybox which uses an OpenGL cube map texture. A sky dome was considered, however it was more performance intensive than the skybox. The skybox had no issues on its edges and was high quality, so I decided to continue development using the skybox. There are various models which are loaded into the scene using the Assimp library. These consist of 6 static and 2 dynamic models rendered using GL draw arrays, as well as additional instanced models, including a particle system which are rendered using GL draw arrays instanced. The dynamic models are a NASA space shuttle which rotates around the y-axis in world space, and a ghost from the Destiny franchise which moves up and down in the motion of a sine wave for more natural movement. The instanced models save on resources by rendering multiple objects in a single draw call. Each instance has its own set of data stored in a struct. Transformation data is randomized within limits, and speed and time are used differently for different models. A for loop feeds instance data into a vector, which is used to create transformation matrices for each instance. The data for instanced ghosts and sparks changes each frame, so the previous data must be deleted to prevent a memory leak, and new data set again before being drawn. Each particle's lifespan is randomly set between 1 and 6. Each instance's time variable is increased each frame, and the particle's position and time is reset when its time is equal to its lifespan. The terrain uses a height map I created in Photoshop. The user can move and look around the scene using the WASD keys and mouse, but cannot move the camera beyond the sides or below the terrain, although there is no upper limit. This was implemented by assigning values to the terrain using an SDL-rect object so that the camera's position can be compared with these values. If the camera's position is at or beyond a boundary, the camera is moved to that boundary. By updating the camera's view and projection matrices immediately after this, it removes any bouncing between positions. Different information can be displayed on the screen using keyboard controls, including an FPS counter and a controls menu. Light color and camera speed and sensitivity can be changed in real time using the buttons on the screen, with lighting data sent to the GPU via a uniform. There is also a minimap in the top left corner of the screen, which displays the player's position relative to the map, and a grayscale effect can be applied to an additional frame buffer which can be toggled on and off. One billboard provides very basic level of detail functionality, as it is rendered in place of a plant once the camera is at least 150 units away, but does not accurately represent the model that it replaces. Models that are not instanced are affected by lighting and fog in real time. Lighting is calculated using the vertex normals of each model. Values for different light attributes determine a texture color, which is passed into the fragment color variable in the fragment shader. For the fog value, the fog color and density are passed into the fragment shader and vertex shaders respectively. The amount of fog is determined by multiplying the fog density by the distance between a model and the camera. The fragment shader uses the GLSL function mix to interpolate between the texture color and fog color, using the fog amount as weighting. Overall, I found this module enjoyable, although it took a good few weeks for me to get to grips with OpenGL. In those first few weeks, I felt that OpenGL was difficult to use due to its long-winded programming process, making it difficult to learn. However, this allows the user to have a lot of control over what they do with OpenGL, so while it is a long process, it is with good reason. I still have a lot to learn about OpenGL, and I'm interested to see what I can do with it in the future. Thank you for watching.